Today we are going to discuss about fundamental theorem of difference calculus. The statement of fundamental theorem says that if f of x is a polynomial of degree n in x, then we have to prove the nth difference of f of x is constant and the n plus 1th difference of f of x is 0. That is, we show that the nth difference of f of x is a constant. The constant is in the form of an into n factorial into h power n. And the n plus 1th difference of f of x is equal to 0. Coming to the proof of fundamental theorem. Consider a polynomial f of x of degree n in x, which is f of x is equal to a0 plus a1x plus a2x square plus and so on plus an x power n, which is a polynomial of degree n in indeterminate x. Now we show that for this polynomial, the nth order difference is constant, and that constant is in the form of an into n factorial into h power n. And the n plus 1th difference of f of x is 0. To show this, we use the mathematical induction on the degree of the polynomial. That is, we are writing here, we prove this result by using mathematical induction on the degree of the polynomial, which is n. So in case 1, if n is equal to 1, then the polynomial f of x is equal to a0 plus a1x. For this polynomial f of x is equal to a0 plus a1x, the nth order difference is considered as delta power n of f of x, that is equal to delta power n means 1, we have taken here, delta power 1 of f of x is equal to, and we know the forward difference operator on any function is defined by f of x plus h minus f of x. The f of x plus h is from f of x. In place of x, we put x plus h in this function. That is a0 plus a1 of x plus h minus a0 plus a1x minus of f of x. a0 plus a1x plus a1h multiply with a1 into x a1x plus a1 into h a1h minus a0 minus of plus minus a1x. On cancellation of same terms having opposite signs, they are a0 plus a0 minus a0 plus a1x minus a1x. You will get the result as a1h. So delta power n of f of x is equal to a1h, and this constant a1h can be represented as a1 into 1 factorial means 1 into h power 1 means h. So delta power 1 of f of x is a1 into 1 factorial into h power 1. And delta power n plus 1 of f of x is equal to delta power 1 plus 1 of f of x, which is equal to delta square of f of x, written by delta of delta fx. Already delta fx is constant. The delta fx is a1 into 1 factorial into h power 1. The derivative of a constant with respect to any variable is 0. So the difference of the constant is 0. So delta power n of f of x is an into n factorial into h power n. Delta power n plus 1 of f of x is equal to 0. In this case, the result is true for n is equal to 1. Now, case 2, induction step. That is, assume that the result is true for n is equal to k. That means delta power k of the polynomial f of x, that kth difference of f of x is ak into k factorial into h power k, which is a constant, and delta power k plus 1 of f of x is 0. So here we are assuming in case 2 the result is true up to kth degree polynomial. Now we go for k plus 1th degree polynomial also it is true. For k plus 1th degree polynomial also it is true. For that case 3, consider n is equal to k plus 1, which is the degree of the polynomial f of x. So f of x is a polynomial taken as a0 plus a1x plus a2x square plus and so on plus ak x power k plus ak plus 1 into x power k plus 1. This is the k plus 1th degree polynomial. Now, for this k plus 1th degree polynomial, we have to do k plus 1th difference of f of x is a constant and k plus 2th the difference of f of x is 0. By considering k plus 1th degree polynomial in x, what we have to show here, we are writing delta power k plus 1 of f of x is equal to ak plus 1 into k plus 1 factorial into h power k plus 1 and delta power k plus 2 of f of x is 0. Consider for delta power k plus 1 of f of x is equal to delta power k plus 1 of f of x is the kth degree polynomial already we have supposed in K. That is a naught plus a1x plus and so on plus ak plus 1 into x power k plus 1. And this delta power k plus 1 of f of x can be written as delta power k of f of x. And this can be rearranged as delta power k of a naught plus a1x plus and so on plus ak x power k. Up to here we can write and separate with bracket and the next term followed by plus delta power k plus 1 into ak plus 1 of x power k plus 1. Delta power k of kth degree polynomial is already by induction hypothesis. It is ak into k factorial into which power k plus it is followed by delta power k into ak plus 1 of x power k plus 1. That is equal to delta is separated to both terms in the bracket. That is delta of ak k factorial into h power k plus delta power k means delta power k plus 1 of ak plus 1 into x power k plus 1. Already we have that for the constant, the next difference is 0. This value is 0. 0 plus remaining delta power k plus 1 into ak plus 1 into x power k plus 1. That is equal to ak plus 1 is the constant not related to delta. So write the constant outside of the delta. ak plus 1 into delta power k plus 1 of x power k plus 1. ak plus 1 into delta power k plus 1 of x power k plus 1 is written as delta power k of delta of x power k plus 1. That is equal to ak plus 1 into delta power k of delta. This is treated as a delta of f of x. Delta of f of x is formula defined by f of x plus h minus f of x. So here we have f of x is x power k plus 1. The f of x plus h is x plus h. In place of x, just simply we put x plus h. X plus h whole power k plus 1 is treated as f of x plus h minus f of x is itself x power k plus 1. Just here we apply the formula of delta of f of x, which is f of x plus h minus f of x. Implies a k plus 1 into delta power k of x plus y whole power n. By using binomial expansion, this can be written as, this bracket can be written as nc0 into x power n into h power 0 plus nc1. This is look like as x plus y whole power n. By binomial expansion, x plus y whole power n can be defined as nc0 into x power n into y power 0 plus nc1 into x power n minus 1 into h power, y power 1 plus nc2 into x power n minus 2 into y power 2 plus and so on. We can write up to ncn. ncn. In place of n, here we suppose k plus 1. ncn into x power n minus n into y power n. In place of y, we supposing h minus remaining x power k plus 1. By binomial expansion, after elaborating this function x plus h whole power k plus 1, we have the reduction as a k plus 1 into delta power k of k plus 1 c 0. NC0 is always 1. H power 0 is 1. And the remaining in this product term, first term, we have only x power k plus 1. 1 into x power k plus 1 into 1. That is x power k plus 1 plus k plus 1 c1 x power k h plus k plus 1 c2 x power k minus 1 h square plus and so on plus h power k plus 1 minus x power k. Here we have in this product term, NCN is 1, x power n minus n is 0, h power n is the remaining. H power k plus 1 remaining minus x power k plus 1. On cancelling the same terms having opposite signs, that are x power k plus 1 minus x power k plus 1, we will have the reduction as delta power k of k plus 1 c1 h into x power k. This k plus 1 c1 into h is entirely considered as a constant into x power k. This is the constant into x power k minus 1 and so on plus h power k plus 1 is a constant. This is treated as a naught. From backside we treated as a naught plus a1x plus and so on plus a n minus 1 into x power n minus 1 k minus 1 plus a k into x power k. So in this bracket, we consider the reduction will be as a kth degree polynomial in x. For kth degree polynomial in x, we have already supposed in the induction step, the kth degree of the kth degree polynomial is a constant. So that here we are writing ak plus 1 into delta power k of kth degree polynomial in this bracket. So by using induction step, we already know that for kth degree polynomial, the kth difference is a constant. And the constant is ak into k factorial into h power k. In this polynomial existence, the leading coefficient is considered as ak, which is placed by k plus 1 c1 into h. So here we are writing k plus 1, this ak plus 1 is followed, k plus 1 c1 into h as constant ak into k factorial into h power k. For kth degree polynomial, the kth order difference is ak. ak is in this polynomial is represented as x power k coefficient, which is taken by k plus 1 c1 into h. That is represented here, k plus 1 c1 h into k factorial into h power k. The next reduction will be ak plus 1 into k plus 1 into k factorial. K plus 1 into k factorial. H power k into h means h power k plus 1. That is written as ak plus 1 into k plus 1 into k factorial can be expressed as k plus 1 factorial, like n factorial is written as n into n minus 1 factorial. So here k plus 1 into k factorial is represented as n into n minus 1 factorial. So we can replace it by n factorial, that is k plus 1 factorial into h power k plus 1. So this is the required one. We have to prove that delta power k plus 1 of f of x is ak plus 1 into k plus 1 factorial into h power k plus 1. So delta power k plus 1 of f of x is a constant, that is proved by ak plus 1, k plus 1 factorial into h power k plus 1. And coming to the next derivative of f of x, that is delta power k plus 2 after k plus 1, the next derivative is k plus 2. Delta power k plus 2 of f of x is equal to delta of delta power k plus 1 of f of x. That is equal to delta of, already we existed here, delta power k plus 1 of f of x is a constant represented by ak plus 1 into k plus 1 factorial into h power k plus 1, which is a constant. So derivative of any constant is 0. So we got delta power k plus 2 of f of x is equal to 0. Therefore, we proved here for n is equal to k plus 1 case, delta power k plus 1 of f of x is a constant represented by ak plus 1 into k plus 1 factorial into h power k plus 1. And delta power k plus 2 of f of x is equal to 0. So if we take n is equal to any positive number, so for n is equal to any finite number, we can prove the result. So in case 3 also, we have proved for n is equal to 8 plus 1. So using mathematical induction, we can prove that delta power n of f of x is constant, which is represented by an into n factorial into h power n. And delta power n plus 1 of f of x is equal to 0. Nth derivative is constant, n plus 1th derivative of the polynomial is 0. Hence the proof. Thank you.